start. The general SVM. So here is some work for you. It's the quiz of the tutorial. I was told it was by the minutes. Okay, so we discuss that later on. So here's the quiz for the audience. There's only one quiz, and it's to see if you have the parameters in mind, because then it's going to evolve quick using those parameters. The question is, if a node is in community I, how many neighbors does it have in expectation in community J? So you have to remember the model how it is. NPI is the number of nodes in each community, and Wij are the connection from community I to J. So here are the possible answers. The first one is n times Pj. The second possible answer is n times Pj times Wij. Then there's n times Pi times Wij. And last is 7. So how many since the answer is question 1? Okay. Question answer 2. Alright, there's some activity. And that was the right answer. I didn't want to make anybody feel bad. So why is that? It's because, of course, there's n Pj potential candidates. You pick each of them is for the Wij. It's like a binomial variable, so that's the expectation. So now this matrix is going to show up many times in the talk. It's the product of the 3 parameters that you have in the stochastic block models. N, P, W. And what it tells you is the expected number of nodes. You each, for example, if you take the ith column here, if you look at what this column contains, it's telling you in expectation how many nodes in each of these communities the node in community I has. Okay? So that's what's called sometimes the connectivity profile. If a node is in community 4, it has, this column tells you how many nodes it has in community 1, 2, 3, 4 in expectation. If you think in terms of channel coding, this is a bit kind of like your channel. What you would like, if 2 nodes, I and I prime, have the same columns, if this matrix contains 2 columns that are exactly the same, then it means that, for example, this community and this one see the exact same connectivity pattern, so there's no hope you can separate those communities. So 2 columns being the same here means the impossibility of distinguishing those symbols, exactly like in channel coding. If 2 bits have the same output distribution, there's no way you can distinguish them. What you would like to understand is what is the right measure of distance among the columns of this matrix, such that you can separate, you can answer that if these are far apart in some notion, then in fact you can separate those communities as well. So mutual information is the answer when you look at the channel, how these distribution have to be far apart from each other. And the question is, what is the right notion of mutual information for this specific problem that we're interested in. So going back to the picture with coding theory, now we sort of try to have the counterpart of the 1 minus entropy of epsilon for this specific channel that was the symmetric case of 2 communities. But channel, of course, has this very nice result that is general. For any W matrix, as long as the rate is below the capacity, which maximizes the mutual information, then you can communicate reliably. So now we don't have the maximization over P, because P, the proportion on the size of the communities, is given by nature. We don't optimize the rates. But could we still have a result of this kind? And as long as I put 1 here again because we're doing fixed rate, as long as some function of P and W is above 1, then you can cluster, otherwise you cannot. That's the question. Is there such a general result? And here is the result we obtained with Colin Sandon, who's my student in Princeton. So the recovery is solvable in the general SVM with prior P on the communities. And again, like in the case of symmetric communities, we're going to look at that scaling, which is the bottleneck scaling, where you multiply the connectivity of a matrix Q, which is symmetric positive, and you multiply all the entries by log n by n. So you can solve that problem if and only if you have this new divergence problem that shows up, where you want the distance between any 2 columns of this matrix. So if you take the product of n, p, q log n by n, then you will have p times q that shows up with this extra log n. So if you just look at how these pq columns are far apart from each other, using the right notion of distance, if they're all at least 1 away from each other, then you can cluster. And the question, of course, is what is the plus? Yes?
Sorry, I know you already generated quiz for us, but I already forgot about
Q in this case is here. Is you connect edges with probability Qij times log n by n. So if a node is in community I and another one is in community J.
Oh, it used to be W.
It used to be W. That's why I call this now Q to show the difference. Yeah. So if those columns are away from each other in this distance notion, then you can cluster. And what is D plus? This is the animal. It's the maximum over some parameter t that is 0, 1. I wrote it down for two measures. These don't have to be probability measures. These are positive measures. So what you take is the arithmetic mixture of the component L of the two measures minus this geometric mixture. And then you do the same over all components. So this is, think of this as being a finite set, a measure on a finite set. So what is this object? It looks like stuff we've seen around in information theory, but not exactly. So first let's call this dt of between mu and nu without the maximization. So if t is half, when you do d half, then this is exactly the arithmetic mean, and this is exactly the geometric mean, which is the same as the Ellinger divergence, or Ellinger distance. You take the square root of each measure, and then you take the L2 norm. That's because arithmetic mean minus geometric mean is just the square of the square roots. So this is exactly what happens in the case of a symmetric block model. The maximizer t is at half because of symmetry. And then you can recover the result that I presented before. This expression becomes half square root of a minus square root of b squared more than 1, and this is the same as the threshold that we had before. A plus b divided by 2 more than 1 plus square root of ab. But it turns out that in many cases, the optimizer is not at half. What's good, and this is, I think, something that at least if you're an information theorist, you should get excited about, is that this is a net divergence. Just like the KL divergence, dt is, you can write it as the second measure times the function, which is convex, of the ratio of the two measures. And here is the function. Instead of being x t log t, like it's x log x, like for the KL divergence, it's this function here. So what does this tell you that it's a net divergence? I guess nothing, except that it's another net divergence like the KL. So it's just, I think, in a sense, cute that the fundamental limit for clustering, just like the fundamental limit for the Lie transmission, is part of the same family of net divergences. But I don't know what else this gives you except a cute fact. Let's continue to try to connect this object to what we know. If you just look at this term, if you forget about these two terms, for example, for probability measures, this is 1. If you just look at the maximizing over t, this term, and you put a log in front, this is what's called a Chernoff divergence. In other words, this object here is a mixture of Ellinger divergence, because it's a bit more because you maximize over t, so it's not exactly Ellinger. It's a bit more than Chernoff because you have this extra term. So we decided to call it the Chernoff-Ellinger divergence because it generalizes both. So now this is just a story of the notation. D plus, you can think of it as the plus is the fact that you maximize over t dt, or the fact that ch means Confédération Helvétique. So this is the same as the Swiss flag, and this is the plus for the Swiss flag. Okay, so now this was just again the information theoretic results. We can cluster if and only if this divergence is above 1. So the real question in a sense is this the right threshold? Can you come up with an algorithm that is efficient, that succeeds whenever you have a CH limit which is above 1? So the answer I thought initially would be no, just because of the conjecture that are taking place in detection. But it turns out that surprisingly the answer is yes. In the case of exact recovery, as opposed to detection, you can come up with an algorithm that achieves the threshold for any number of communities and for any size and for any connectivity pattern. So that's the algorithm that we obtain is called, we call it degree profiling. I'll explain it in a second. And not only that achieves the threshold, but it actually manages to do so at quasi-linear complexity. So it's not an SDP-based algorithm. And here really getting something efficient was really not obvious, but maybe quasi-linear is really the effort of calling. Did a great job on that. So a quick comment about this. If you don't want to extract all the communities, that's really a strong requirement. If you just say, I care about extracting a special community, Then what you do is you represent each of your columns into a point in R to the power k. So these are just points in the Euclidean space. They are nothing to do with the graph that you're trying to cluster. They are abstract representation of each community. There's k of them. If the ith community point, that what you represent the community with, is at distance 1 from all the others, even if some of these other guys are less than distance 1, but if this one is isolated, then you can extract it. So that's another result. And a quick comment on the fact that I'm assuming throughout the entire talk that we know these P's and W's, these P's and Q's. Obviously, you never know P and Q in application. So this was the problem of whether you can do the same without knowing the parameters. So I will not discuss it today, but we just posted the paper yesterday on arXiv, and it turns out that you can actually redo everything without knowing the parameters. Even if you don't know the number of communities, if all you assume is that the communities are of linear size, so there's a relative size, those PIs are bounded, then you can learn the number of communities and you can redo the results that I'm describing without knowing the parameters. So you can learn the block model on the fly. So now I think to finish on time, I have to a little bit pick what I'm going to discuss. So here is an important step. How you achieve the capacity in the case of the general stochastic block model. That's somehow the key, the root lemma that tells you why the CH divergence is the right answer. Imagine that someone gives you the right clustering. So this is the graph with the right roots, and there's a bunch of edges across that I don't draw. And now someone takes a node here, which is in community 1, and it looks at dv, that's node v. dv is what I call the degree profile. It's how many nodes it's connected to in each community. Okay. So what is the distribution of dv? From the quiz, we know that it's log n times the PQ, the first column of the matrix PQ. That was exactly the quiz. I put a little dot here because it's approximately a Poisson distribution. It should be a binomial distribution, but in that regime it behaves like a Poisson. And now if you look at another node which is in the community 2, just with the same reasoning, it's going to be again a Poisson, but now the mean is a vector which is given by the second column of the matrix PQ. All of this scaled by log n. So look at the following problem, which is not the problem that we try to solve. It's a much easier problem. But if someone gives you exactly the right clustering, the answer to what you're trying to solve, but now it just takes one dot in one of the communities and it puts it in the middle without telling you where it came from. So it's just hiding one node. But it shows you its degree profile. It shows you how it's connected to each of these groups. If you try now to put back that node where it belongs to, you're trying to solve an hypothesis testing problem. There's a k hypothesis, in this case 3 hypotheses. And here I just wrote 2. And you try to distinguish between those different measures. That's exactly the problem. Between those multivariate Poisson distribution, when can you decide where it comes from? So this will have an error probability. And we worked out what is the error probability of that test. That means you have to control the mass in the overlap of these two multivariate Poisson. And again, it scales polynomially with an exponent, which is exactly that CH divergence. And these are the vectors of your Poisson, and this is the error of the map test, the overlap between the two Poissons. So because you scale by log n, the mean, you only get the polynomial scaling. Surprisingly, we didn't find that result in the literature. I wouldn't be surprised that the paper on the 60s has this found, because it seems to be a very neat result that is not very hard to get. But if anybody knows the result, I'll be happy to learn about it. So now, why is this interesting? Because it tells you the following plan. Instead of trying to recover the communities as an SDP or a method which is achieving the threshold in one shot, which is typically very hard. Like if you try to prove that SDP works in a generalized EM, I don't know exactly how to write the SDP, and then you have to deal with random matrices that are non-standard, and I would have no clue how to prove that this works. It's probably possible, but I would not know how to do it. But this tells you another plan, which is that instead of directly in one shot trying to get the communities, try to come up with a reconstruction which is not too bad. Let's say it's 95% correct or 99% correct, but you're a little bit wrong. And then what you're going to do is do this kind of procedure that I described to you. You're going to try to reclassify nodes only based on their local neighborhoods. In other words, you take your pre-solution, which is a little bit wrong, and then you clean it up by doing those local checks, this hypothesis testing problem. So this is the idea behind the degree profiling algorithm that achieves capacity. You take your network and you split your network into two other graphs, G prime and G prime prime. I'm going to make the degree of G prime to be roughly of degree log n. You will see why in a second. And G double prime stays of degree roughly log n. And what you do is on the first graph, you run an algorithm that I will discuss next that gets you not everybody correct, but almost everybody correct. So you're a little bit wrong. So the block error probability does not go to 0 for this algorithm. However, then what you do is you actually use that clustering from that G prime graph. You use it as a seed to do the problem that I described to you before. So I added those boundaries here that are red because that means you're trying to redo what I did in the previous slide, except that you are slightly off by some percentage. But if you are away from the threshold, you can tolerate that little error. And if you do the test the way I described it before, even if you have this little error, you still distinguish and you can reclassify those nodes based on their degree profile. So that's the general mechanism of the algorithm. So the question is, how do we get most nodes correctly? So now I'm going to start discussing other recovery requirements because we don't want to get everybody right, but we want to get maybe 99% or maybe even 70%. So partial recovery is in a sense the general recovery requirements. We say an algorithm solves partial recovery if it with an accuracy of alpha, so alpha is a number between 0 and 1, if it produces a clustering which is correct on a fraction alpha of the nodes. And all the statements are always with high probability when n tends to infinity. So exact recovery is just alpha is 1. You want everybody correct. Block error probability goes to 0. Now I'm introducing what I call here almost exact recovery, that the statistician called strong consistency. There it's when you're asking that you get a 1 minus little o of 1. So in the limit, you have a fraction of node which is wrong, which is vanishing. And then you have the weaker recovery requirement, which is detection, where you want to just beat the random guess. So if you have k-symmetric communities, the random guess gets you 1 over k, you want to be a little bit better than that. Why do I only write detection for a symmetric case? Because if you have asymmetric communities, which are larger degrees or different size, it's always possible to detect just by looking at degrees or sizes. So in a sense, detection is meaningful in the symmetric case. Now, for all of these recovery requirements, one can ask the question, what are the fundamental limits, both information theoretic and computational? We basically have the answer for the general SBM with linear communities for the last two. That's what I'm going to tell you today. But the first two are still open. We have the first for 2 communities, but not for 3 anymore. And here we have basically little clue of what's happening for partial recovery. So, next thing that is important to have perhaps at this point is the notion of signal-to-noise ratio. Right? In information theory, all our results are based on the SNR. So what would be a good notion of SNR for this model? So because I'm going to talk about partial recovery now, we're looking at this regime where the W is Q by N. So we no longer have that extra log N factor. The extra log N is there to allow you to do exact recovery. But now I'm going to be only happy with 70% correct, for example. So I can tolerate a constant degree regime, Q by N. So if you do the quiz here, you do the product of these three, now P times Q is exactly your expected degree for each node. So here is the notion of SNR that we propose in the paper with Colin, is a ratio between, so you take the eigenvalues of the matrix PQ, and you take the minimal eigenvalue, because this is not a symmetric matrix necessarily, it's a complex number, so you take the magnitude, you square it, and you normalize by the largest eigenvalue. So the largest eigenvalue is always a real because the entries are positive. That's why I don't put the magnitude. So why is this a good notion of SNR? So first of all, what does it mean in terms of 2 symmetric communities? In that special case, this exactly reduces to the ratio that shows up in the detection result that I presented previously. So if that SNR is more than 1, you can hope to detect. And now the question is that if you are above 1, how much can you detect? That's partial recovery. And a quick insight is that if you have 2 symmetric communities, if you take a node, it's roughly connected, we said, with a binomial variable inside its community, and there's another binomial variable for the number of neighbors outside its community. If you don't have the extra log n, if you are in this regime now of constant degrees, then this is no longer atypical. It has a positive probability to be wrong, that you have more node in here and here. If you look at the expectation of the gap of these 2 random variables, divided by the standard deviation, so this is a natural notion of SNR, it's exactly that ratio. We'll see another interpretation of that ratio in terms of a broadcasting problem. Okay, so now we have another algorithm, that's a second theorem, which we call sphere comparison. So that in that sparse stochastic block model, without the log n, the algorithm recovers almost everybody when the SNR goes to infinity. And in fact, if you have a symmetric block model, it's also necessary that the SNR goes to infinity in order to have almost exact recovery. So in a sense, this SNR is the right notion of SNR if you want to understand when you can or cannot have almost exact recovery. We also have a result in the paper which is when you only want to get a fixed percentage, but I will not discuss this here because it's probably a little bit technical. So now, why is this helpful for the program that we have with degree profiling? It's helpful because if you look at the SNR notion, if you scale all the entries of Q, if you multiply them by C, then the eigenvalues scale by C. So this ratio is the SNR is scaled by C. In other words, if you have now an extra log again in front of here, then the SNR will go to infinity. So we will be in that regime where SNR diverges, and then we can recover almost everybody. We can plug this into the black box of the previous algorithm, and then we can finish with the local checks. So that's the general approach. So I'll skip the explanation of the sphere comparison algorithm. The rough idea is the following. You start with the quiz. The expected number of nodes is the ith column of p times q. Now, you cannot do any inference by looking at the neighbors of a node in the graph because it's a Poisson of a fixed mean. So there's fluctuation. There's no way to predict things by looking. There's like 3 or 4 neighbors. But if you start looking at the neighbors of neighbors, then eventually this grows. And you can perhaps hope to do some inference by observing the neighbors of neighbors of neighbors of the large enough depths. So if you look at the node in community I, the way its neighbors at steps R, after you look at the R distance neighbors, is going to behave like taking the matrix PQ, putting it to the power R, because you are concatenating these channels, and looking at the ith column. So you're taking just powers of your matrix to understand what's happening at the depths R. So now, of course, if I tell you how many neighbors this node has, it's not enough to tell me what the community is here. For example, if you have a symmetric block model, this is exactly the same for both communities. But the idea is that instead of looking at of how many neighbors a node has at a given depth, you count how many common neighbors 2 nodes have at a given depth. Think of the intuition, if you are 2 nodes in the same community, like 2 Republicans, you're likely to have much more common neighbors than if you look at the Republican and the Democrats. So the goal is to try to do inference on that, and that's the idea of sphere comparison. You're comparing the sphere and the common neighbors you have. Okay, there's quite a few subtleties that I'm going to skip here because you have to come up with some independence to analyze this, and to make it quasi-linear, you have to work a little bit harder. So that's jumping to the conclusion that that's the general spirit of the algorithm. Compare your spheres and try to deduce from that if those nodes are in the same group or not. Okay, so now I just wanted to give you at least one real example with data. You could probably do a whole tutorial just on data implementations, but here is an example on how you can use the information link thinking on real data. So that's the blog network. It's a very popular network in community detection. It's about 1,500 blogs. They're either Republican or Democrats, and what you observe in that data set is you have no clue about the content of the blogs. You know nothing. All you know is which blog has put a hyperlink to another blog. And you ignore also the directions. That gives you a graph. Each node in the graph is a blog, and 2 nodes are connected if they are referring to each other. If one at least refers to the other. Okay, so now, is there a block model behind this data set? Probably not, but maybe not too far from a block model, from the one we discussed before. But let's assume that you are maybe silly and you assume that there was in fact a block model with 2 communities behind that model. So then, because you know the ground truth here, I computed what would be the parameters, this matrix P times Q that we work with. And this is what it looks like. It's almost symmetric, but not quite. And it has, of course, more connectivity inside the cluster than across the clusters. That's your channel. Then you can compute the CH divergence of that matrix, and you get something which is 1.5. So even if, whether you are wrong or not, like fitting a block model on these data sets, at least what this tells you is that because the CH divergence is more than 1, if this were to be a block model, then you could hope to recover the communities. If this would have been 0.01, then it means that that data set, if you wanted to fit it with a block model, you should not hope to recover much. So that's kind of the new insight that the fundamental limit tells you here. And why the constant matters, because this could behave differently depending on the parameters you have, up to constants. It could be a very big difference. So now we tried our algorithms and we got 95% correct. So which is a lot. In other words, you only know who refers to who, nothing about the block contents, but with 95% accuracy, you can tell which block is Republican and which block is Democrat. That's not a big surprise. If you look at the state-of-the-art algorithm in this business, they all get close to 95. So the naive methods get more in the 80%, 85%. The most sophisticated methods go to 95%. I think that's the state-of-the-art, 95%. But really what I prefer instead of getting 95% is that little story here, which is in the same new. This kind of vignettes that the algorithm could predict something. So, open problem. That's probably something that matters, yes?
So I think it's a good example. Of actually, there's more information, right? For example, here the edges are Boolean. Either they have a hyperlink between two blocks or not. Maybe we can count how many links there are over the relation.
Very good. That's very good. That's going to be in the open problems. So thank you for the transitions. So before I get to what you said, so first series of open problem is about the stochastic block model in the basic model that we discussed until now, and then I will get into those other extensions of the block model. So the first one is a recovery, so the exact recovery problem. So you can discuss the case where the number of communities grows. Our result extends until k, which is logarithmic. Beyond that, you need probably some new techniques. There's a very nice paper of Chen and Xu that studies scaling that are polynomial between those parameters QP and Q, KP and Q. But they don't study the phase transition, but it identifies some computational values. So let me go maybe to the most interesting one. So yeah, this one is very nice, the detection and the connection to broadcasting. So that's nice for information theories because broadcasting is something we are familiar with. So quickly, why is detection impossible if you don't have this ratio more than 1? That's the paper of Moser, Niemann, and Sly. So again, you look at the neighborhood of a node. So take a node in a neighborhood of size, let's say log n, so nearby, because you have a sparse network, this is like a tree. So what is the number of neighbors you have? This is a quiz, it's a plus b by 2 in this way, in this case. It's Poisson because in the regime we are, the binomial behave like Poisson. So first you can deduce that if a plus b by 2 was less than 1, this tree process will die with higher risk probability, which is 1. So that's where the regime where you don't have a giant component. So basically this is the graph looks like a bunch of disconnected groups, there's no hope to recover. So you need at least a plus b by 2 to be more than 1. So in fact that's necessary to detect. But now, to care about the detection problem in this model, you don't want to study just the probabilities of the graph, but you want to study the following broadcasting problem. You put a bit at the root, that's XR for roots, it's 0, 1 with probability half. And then you broadcast it there. So you send it through each link here is a BSC channel. Why is the parameter B divided by A plus B? Well, if this is a 0, it connects with probability proportional to A in the same group and to, so it connects with the probability proportional to A to a node in the same community and B in the other communities. So the flip probability, the probability that you go to the other side, is a proportion to B, that's why it must be B divided by A plus B. So you have now, even if you are lost at this point, forget about the block model, just think of this as a very clean information theory problem. You take a bit, you broadcast it to Poisson with a mean C, children, with BSC with a parameter epsilon. Forget what epsilon and C is. It's a broadcasting problem, and you keep doing this for many generations. And then you ask, when I observe the leaves only of this broadcasting problem, when can I reconstruct the roots? So again, the word unorthodox shows up here. I think unorthodox is probably the word that we said the most with Martin throughout the tutorial, because that's somehow the conclusion of this tutorial, that machine learning is like coding theory, but in an unorthodox way. Here it's unorthodox because you try not to reconstruct the bit at the roots with probability that tends to 1, that's what we would do in information theory. But here you just want to reconstruct the bit with probability better than half. That's a detection problem. So I don't know many people who study this in information theory. But this turns out to be what you want for understanding detection in this model. And this was actually solved in the 2000 by Evans, Kenyon, Pearce, and Schulman. And what they found is that if the number of children you have, C, is more than this ratio where epsilon is the noise parameter, so it's B by A plus B in this example, then you can detect, otherwise you cannot. Sharp phase transition. And if you plug C and epsilon to be those parameters, then it's exactly the threshold here. That's the insight of why this threshold tells you why detection. So what is the connection between the broadcasting problem and the detection in the block model? You cannot see why it's clearly giving you the achievability part, but you can see why it gives you the converse. Because the converse works with a Gini type of argument. If you had a Gini that told you the value of the leaves in the neighborhood of a node in the broadcast in the network problem, then if you fail reconstructing the roots with better than half accuracy with the Gini, there's no hope that you succeed without the Gini. That's the type of argument. So that is a reduction to this problem for which you can prove a converse. Now what's happening is if you have k clusters instead of 2 clusters, the SNR is going to be this. That's the ratio of the max eigenvalue and the mean eigenvalue that was defined previously. And here there's a very interesting conjecture that happens, that was done in a conjecture in the paper of Dessel et al., which is that there seems to be a computational barrier. If the SNR is less than 1, it's possible to reconstruct. But there's another constant Ck, for which if you go between Ck and 1, it's only possible informationally but not efficiently. But this gap, this computational barrier, seems to happen only when you have 5 or more communities. Up to 4, it seems like Ck is equal to 1. And this connects to the fact that this broadcasting problem that I mentioned previously, we don't understand what's happening when you have more than bits, when you have query bits, like ternary or quaternary. There are some results for ternary, I think, but surely for symbols of an alphabet of size 5, we don't understand what's happening exactly for detection. So there's a lot of work to be done here. Another very interesting question which naturally connects to information theory is what would be the rate distortion theory of these problems. If now you don't want to just detect, but you ask how much distortion can I have, then I conjecture that this is a natural extension of the previous conjecture. If you plug here the distortion, so it's 1 minus the accuracy of the reconstruction, if SNR is above 1, I'm plotting here what's happening for 2 communities. Well, below 1, the distortion is half because you cannot even detect, so you may as well do a random guess. But above 1, there seems to be a curve that tells you how much you can reconstruct. So that's the percentage you can get on distortion given the amount of SNR you have in the problem. But we don't know what this curve is. So in the booklet that is on our webpage, I discussed the partial result about establishing this curve, but in general, we don't know what it is. So that's open. And for K more than 5, there's probably a gap. Okay, so other block models. So the first one is what's called labeled block models. So this is where you have a label on the edges. For example, intensities of connections. So one should be able to redo all the things that have been discussed in this case, and you get more information. There is some result already on that. One special case of block model is the sensor block model, which is, I think I'm going to skip it. Let's see, what time is it? So this is, we started at 4:15 after the break, so this is... Okay, so I'll skip the sensor block model. We proposed it recently, but it connects to many work that other people have done. It's a pretty natural problem, and there's been quite a bit of progress recently, also from people in our community. But let me just focus on the last part of the talk. So the recorrelated block model is the fact where you also take into account variation of the node degrees. Mixed membership is when you allow for overlaps in the communities. Blended community problems, that's where you have one community which is much smaller and much denser connections. So that's just another block model, but in a special format. And hypergraph models, these are all extensions. And for all of these extensions that are very important for applications, all the questions we discussed previously take place. Is there another F divergence that captures when you can recover? Is there some SNR distortion curves in detection, etc.? So this is roughly open. Partial results are mentioned in the booklets. So beyond block models, graphons. I don't know how many of you have heard about graphons, but in a sense, it's the limit of stochastic block models, where the variables of the nodes are not discrete; they are continuous in 0, 1. And then you put edges between any two nodes, depending on a kernel, just like we had before, but it is now continuous. It takes those two numbers and now it is 0, 1. So what is very nice with graphon is that there's a beautiful theory that tells you that, first of all, the limit of most graph sequences, if they converge, are behaving like graphons. And also the stochastic block model, in a sense, acts like an approximation of graphons under some regularities. You can represent graphons by piecewise linear block. Piecewise representation is exactly what the block model does. And then there's the graphical channel. That's a model we proposed with Andrea Montanari a couple of years back. We just tried to come up with a model that captures pretty much all the examples we discussed today in the information-theoretic type of language. So it's a model where you have a channel, and instead of taking an arbitrary code, you just have the XOR, or not the XOR, but you just take a few local bits. So the number of nodes you can take at each channel is only k. And then you have a product measure, the edge variable e, so ye is the edge variable for edge e, depends only on the incident nodes, and this is bounding. So this is just a model that captures the locality phenomena that we saw in all these applications. It's also related to a model by Lafferty on what's called conditional random fields. So what I want to say here is the following. This is a specific type of graph on a channel. One could ask, is it possible that this normalized mutual information always converges, in fact concentrates? This seems to be very natural, and this seems to be true for all possible Q you can think of, and for G, which is enough uniform, like an area Shreni graph, but it seems to be very hard to prove. We only have the proof for some special cases, like of symmetric kernels, but symmetry seems to be artificial. So for some reason, we don't have the right tools for that. And then you can redo covariant Thomas for graphical channels. Instead of having random codes, you have a specific code, which is this graph. But it seems like most questions still go through error exponents, scaling laws, etc. Okay, so that's the last slide, or last two slides. Is the closing the loop and connecting these block models and this problem of clusterings to sparse PCA that was discussed by Martin previously. So here is the Spike-Wigner model, slightly simplified. I got rid of some parameters, so P is equal to N in this model. You have a vector X, you take XX transpose, that's a rank 1 matrix, that's the SNR here, and you add a Wigner matrix, Gaussian matrix with IID components outside of the diagonal, above diagonal, and symmetric. So now, what is sparse PCA is when you have this X which is sparse. For example, a simple case, it's IID Bernoulli epsilon. So that means that most of this component, for example, could be 0 if you take epsilon to be vanishing. So in the paper, in the Wainwright, they discuss when you can hope to recover exactly X. That would be exact recovery. And this happens if epsilon is vanishing roughly like n by log n. And Deshpande Montanari discussed the same problem where when epsilon is constant, so you cannot hope for exact recovery, but again you have the detection type of problem, where the MMSE is studied and they found the information threshold for this problem. So is this a graphical channel? Is sparse PCA of the kind of the problem we discussed before? What is your guess? Yes, because it's just the Yij component that you observe here is just the product of the two Xij plus some Gaussian noise. So it is in fact some noisy observation of the local interactions of only 2 bits. What's unusual is that you are taking product of bits. Here I'm not using plus minus 1, I'm really using bits for sparse PCA. So it's unusual because it's not like in the SBM where this will be plus minus 1s, and it's also a continuous noise model. But it's not too far from what we know. For example, in information theory, instead of having the BSC, we can do binary input over Gaussian noise channel. That's a bit this kind of extension you have here. So if you change the model, and if you say that instead of Xi's being Bernoulli, if you make them Rademacher, meaning plus minus 1 is probably half, then this is exactly the type of prior you would have in the stochastic block models, roughly 2 groups of equal size, and then you perturb them with some Gaussian noise. So this is a new model that, in a sense, is very similar to sparse PCA. It's a spiked block Wigner model where the X are not Bernoulli but are Rademacher, plus minus 1. So now this low rank matrix recovery problem looks like the stochastic block model with 2 communities, except that you have Gaussian noise. So you don't, in the block model, the noise is symmetric. It makes you go back to 0, 1. It's just a discrete noise. Here it's a Gaussian noise. But one could ask, are those models really different or are they the same? So in some regimes, they are the same, perhaps. And let's try to measure being the same with mutual information. If you take the G graph of the block model with P and Q, and if you take the Y model with the spiked block Wigner model, you could ask when are those behaving the same in the limit of large n? Meaning when is the information in one about the same as the information in the other one? And this is a paper that is going to be posted next week. We just finished it with Andrea and Yash Deshpande. It tells you that if you have this regime, which is a little bit odd, the regime, it's not the one we saw in the previous work, where the SNR, that's the SNR notion we have in all the previous slides, is going to a constant, so it's finite SNR, but where the degrees go to infinity. So you're making basically the ratio and the nominator and denominator go to infinite with the same ratio. So in that specific regime, then in fact, those two models are equivalent. In other words, clustering in the stochastic block model and sparse blocked PCA are behaving the same way. Gaussian noise is effectively what's happening in this model. So this is useful not just because it creates a nice connection between the two problems, but also because we know much more about Gaussian noise than discrete things for some aspects. So in particular, yes?
Sorry, this is something to story. Because earlier I asked you that is mutual information the right quantity, and you said no. And now we're back to mutual information.
No, because before you asked me about the mutual information of the one-shot channel. Here I'm looking at the mutual information of the blocks, and I'm normalizing by n. So that is probably the right quantity, but it won't be scaling like the one-shot. So now, here is the thing, because you can connect the block model in that regime to the Gaussian noise model, we could use more and could actually compute that limit. And what is the object? So there are some fixed point here equation. So gamma plus is the fixed point of this equation where you have an NMSE formula for this one-shot channel. So this is kind of the punchline. This is not a one-shot problem, this is a block problem. The normalized mutual information of this block problem, you can express it as the one-shot of this other channel where you have a radar curve by Gaussian noise. But the scaling that you have here, this gamma is highly non-trivial. Is the solution of this fixed point equation with the NMSE of the channel. So this is not something that I would typically have guessed, unless you know how these things work. So now if you and what is this expression you have in the limit? It's still the mutual information, but of the gamma at that fixed point. So if there are coding theorists in the room, they probably have an idea of what's going on behind here. What we use is an area theorem, like in the G-exit type of proof. And then we show that the derivative of this object, which is related to the NMSE through the famous formula of I NMSE of Guo, Sharma, and Verdu, allows us to connect, and then we get a fixed point equation. So skipping the details, but that's basically how you can get the expression, and there's also an algorithm that achieves the limits efficiently, which is the ANP algorithm. Okay, so over time, I'll conclude just by saying that I hope I convince you that committee detection coupled naturally with information encoding theory problems. So we saw a few connections with, of course, graph-based codes is probably the core. It's really a special type of coding theory. F divergences, not necessarily KL, but other type of F divergences. Broadcasting problem, and information estimation problem, like INMSE formula ends up being crucial in the last paper. Or unorthodox version is really the keyword here. Don't expect to just take your tools and directly apply them. And that's also why I think it's fun. It's fun because it would be boring if you could just take all the tools we know in coding problems and directly apply them. But the fact you have to tweak them and understand how they adapt is what I think is exciting. And the more general statement is that many problems in machine learning seems to be dealing with this inverse problem of going from local to local interaction to global properties. And information theory seems to be both needed because it does to give benchmarks to test algorithms and understanding which algorithms are better than others, and powerful because we can solve problems that were not solved before that. I think that's the end, and there's a reception, and there's a booklet, so a PDF document about the two parts of the tutorial on my webpage, and probably Martin will do it. Thank you.